We're good. Oh, we got the okay. So I moved the lab report to Friday. I don't know if you saw that on the thing, and I didn't make it as a submission. I didn't make that as a submission to the. Let's follow me to the to Canvas. Just print them out and hand them to me. And if they're in the lab, I'll just pick them up at 5 o'clock on Friday, and then I'll start grading them over the weekend. Okay. So I sent out some guidelines for that, or it's on they're linked up to the thing. A couple of things that I want to make sure that you know, though. One is you're practicing. Okay, you're not going to change the world with this lab report. All right, so you're practicing how to change the world with a future publication. Okay, so I don't really care that much. That's a bad way to say it, but I don't really care that much if you write me a procedure on TLC and everyone else wrote a procedure on extraction. I mean, it doesn't matter to me. Okay, but I want you to write up one procedure.
What have you already done before?
Turn them all in. All grade 1. Good. Remember why we're doing this. It's good practice.
Yes.
Right? So, okay. So I'm going to give one of them scrutiny. All right? Yeah.
That procedure, are you looking for like step by step, or are you looking for like a paragraph, how to go about doing it?
There's an example on the thing, and look up some example procedures. And I'm looking. This is the criteria to get an A on the procedure. Someone else can take your procedure and reproduce your experiment exactly. That's the criteria. Okay, it's simple, but I'll show you ways in which people interpret what you'll say differently. That's my job. Okay, and then so that's really the only thing. And then in general, just write in general terms about separations and those sorts of things. It's just I don't need to grade 5 or 4 or however many there were procedures. I'm just going to grade 1. Okay, if you want to put them all in there, that's great. No extra points, but put them all in there. And then, but what I really want you to do, so, okay. I've been a professor long enough to know that if I give someone a grade and put a whole bunch of stuff on the marks, if I don't hold you accountable to those marks that I put, sometimes students don't even look at them. They go, "Oh, I got an 85. I'm good with that," and that'll be great. Let's just say that's what you're good with. I'm not being judgmental. Okay, and then you won't look at all the marks that I gave. Well, darn, why don't I just give you a score and not give you any marks, right? I mean, from my perspective. Just because there's those 3 people in there that want to look at all the marks that I give. So I really do want you to look to see why you got points missing and try to absorb it. Okay, this might be your first chance of writing a lab report because you didn't in Gen Chem, right?
Yeah, we did every time.
Okay, but they didn't. You didn't. Were they just like a 1-page type thing?
No, they were 6 pages.
They're like 6 pages? Oh, so you know what you're doing then. Just do that. Okay, 1 procedure. I'll grade it. We're good then. We're all set. I was under the assumption you didn't do them last year.
So we did the intro, we did the procedure, what we're going to do, the data collected. And
it's all on that sheet that I posted up. That's the standard lab thing. And whether or not you put the procedure in the body or at the end, that just depends on the type of journal article that you'd be writing. So some journal articles actually have you put the procedures in the footnotes. There's all sorts of different ways of organizing those, but the main thing is you're going to have an introduction, you're going to have an abstract, okay? An introduction. You're going to have a discussion section, which is, sort of a talking about the procedures, talking about what you did, and then you'll have to have a conclusion and a results section. So you'll have to take. Here's another one. I don't need everybody. So whatever the procedure is, do the results. Just do one of them, and these need to match up. So whatever your procedure and results are, just pick one, because I don't need to look at all of your results. Okay, because here again, I'm just judging you on whether or not and how you do this. Yeah.
I have two quick questions. One, so for the simple and fractional distillation, we each, like I did one and then Amy did the other one. So am I writing about?
If you choose, so if you're gonna, that will not matter, because there again, you choose the one that you did. You write up the one that you did. Okay. And if they're different, that's okay.
Okay. And then also, the rubric that you posted on Canvas talks about the abstract, which we did not do last year.
You'll do an abstract.
It also, it has a lot of details, but then says you're not going to really closely grade it. Can you go into a little more detail what you're expecting in the abstract?
No, not really, because it's going to be experimental. You're going to write me an abstract, and then I'm going to tell you what goes in an abstract. It's really hard for me to tell you. An abstract, have you ever read an abstract? That's what an abstract is. Who's not read an abstract? Go read one. Every abstract for every publication is available online. Go to PubMed, read an abstract. You know exactly what's in that paper when you read an abstract.
You also want us to do like the Chem Finder and find a paper to attach?
No, I put that in the body of my announcement. You don't have to do the Chem Finder part. We'll do that later. What I would like you to do is come up with figure out if you can do it. And if you do this the night before, you're going to fail. Okay, so if you do this part, you may be able to write all night long and it'll be fine. But if you do this part the night before, you'll come to me and say, I couldn't get it to work. And I'm going to say, okay, what do you want me to do? Everybody else got it to work. So go in and find one of those free drawing programs. So there's a couple of them, and I put them on this thing. There's just search them. Organic chemical drawing programs, free. I use the Marvin Sketch one. That's how I write your exams. That's the one I use. It's completely free. It runs on my Mac just perfectly. So if you download it and can't get it to run, I can't help you with that because you have some setting on your Mac that isn't right. So you're going to have to troubleshoot that in some way. That's just reality. And then if you have a PC, I think it's the ACD one works.
If you use ChemSketch on Windows, I can help you with that because I use ChemSketch.
ChemSketch on Windows, okay? And if somebody gets it to work and you can't get it to work, you can use their computer and do your sketches and then export the file. Just copy, paste it into a Word document and send it to yourself or a Google document or something. Yeah.
Are they, is it a program you download or
yeah.
is it just like a website you go to?
Right. Correct. ACD. Yes.
Are these for like drawing out your the compounds that you use and showing them in your paper? Is that what this is for?
Mm-hmm. Versus drawing them versus hand drawing them. Just want to get you into the practice and knowing that you can do that. So later down the road, you're given a presentation, and there happens to be an organic molecule on that presentation, and you're like, oh, I'll just grab one from Wikipedia. Well, then it's up on your thing, and it's got the Wikipedia stamp on it, and it doesn't look very good. Yeah.
Hi, so for the simple or the fractional distillation, you know how we made a graph.
Excel.
Yeah, is Excel fine or something? For displaying those results.
Yeah, whatever that. Don't handwrite them out.
Okay, just making
Is that what you're saying?
I'm just saying, is there any specific thing you want us to use for that, or is Excel fine?
Do not use graph paper. I'm not even sure you can find graph paper anymore. You can print it out on Excel, I know. Don't do that. This first one, right? I'm going to grade it. This may be your first one that's been graded. Let's think about this. I have almost 40 of you, and I'm going to grade this. This is how important I think it is. Okay? Yes.
So, do we need the chem sketch for this one?
Yes.
Okay.
Yes. But not the night before.
Right.
So like sometime before then. Okay. So it's due Friday. Probably because I'll let you know at the end of the class today whether or not we're going to have the quiz on Wednesday or Friday, because I'm not really sure where we're at. Don't do Friday? Do Friday. I'm not going to take a poll because it'll be independent for all of you. This is like, you guys are so used to this, such personal care.
Yeah, I have 3 exams.
Next week?
Please do next week. Jesus would do next week.
What would Jesus do?
I would just look into your brain and know what grade to give you.
That's not Jesus. If we're going based off of Friday,
Go and study. Go and study no more. Go and study more. So, what's this week? Is this midterm week?
Yes.
How many exams? So if we had the quiz on Monday, what does that do to you?
That'd make me happy.
Raise your hand if Monday makes you happy.
Also, we are taking a poll now.
Okay, raise your hand if Monday makes you really, really, really sad. Okay, so we'll go Monday on the quiz then. Okay. All right. Remember these sorts of things when evaluations come out.
Okay.
I mean, do I need to remind you of all this stuff like right before those come out? Or can you remember this? I want you guys to do well and concentrate on the things you have. It's also really important to be stressed out, because you learn how to deal with stress.
Oh, we have plenty of
You don't really realize how much stress you'll be under in life.
We have an exam this Friday.
You probably know, right? So I'll tell you another little personal story. The worst evaluations I received from any class, okay, was an organic chemistry class a number of years ago. You don't know any of them. The absolute worst evaluation that I received ever on, that I can remember, and I look at them all and I analyze them all, was the spring semester that my wife had cancer. So I know stuff happens in life. I know there's all sorts of things that take place. That's all I could do. I mean, I know that I shortchanged that class. But that's the best I could do at that time. I couldn't be as responsive to things. I was running my wife back and forth to hospitals for surgeries and checkups and all sorts of things that you have to do when you have little kids and your wife has cancer, and that's important. It was more important than that organic chemistry class. Oh, I should have blocked that out. But, to me it was. So in a sense, that was a failure for me, and that I was at a point where I could not juggle everything, and things fell off the plate, and I did fail at certain things. I don't think I hurt that class, but I probably didn't give them as much attention as they had thought that I should give them. So in life, you'll have those times. It may be right now. I mean, I know that a lot of you go through some pretty difficult things at times. And, it's what I always like to, with you and with my colleagues and with my church friends and with whoever they are, you should always give someone, and I don't really care what you give me on my evaluations, by the way. They come to me, all right? I'm not going to fire myself, all right? So they can say, go do something else or whatever. But I do care because I want to make the class better. That's why I do it. So I'm not saying this to get good evaluations. I want you to give me good, honest evaluations. Where was I going with this?
Something about us you being nice to us.
Give other people the benefit of the doubt. I just wish that in society we would do that more. Give someone else the benefit of the doubt. Something comes up, it's your roommate, whatever it is, just don't react to it. Let it sit for a while. Ask them what's going on later. Whatever it is. If you see something runs through on your email about a sports figure, how quick are we to jump on a bandwagon and judge what happens to these guys? I guess it's fun and it's entertainment, but it's hurtful to them as well. Sports athletes do not, the good ones don't even look at the press because it's all negative about them. What if we had a society that, just gave others the benefit of the doubt on everything? Now, if you commit murder, you don't get the benefit of the doubt. But, everybody has a bad day. Everybody has a time in life in which things aren't, perfect and cruising. In fact, that's some of the best times of life is when you're having to rethink things, rethink where you're at, rethink the decisions that you've made. Those are important times in life. So, okay. So there, make sure you say that I do devotionals. So, all right. Okay, next thing. There is a small amount of seminar points. Seminar. Okay, I should have recorded Friday. We should have figured out a way to record Friday's lecture. I mean, I should have given the stuff to Andrew and he could have done it, but I was busy and off to a conference. If you remember, did Kyle talk about what his graduate work?
Yes.
Yeah.
Okay.
We had 3 minutes to go over that part though.
Oh,
So
about what?
He drew the whole diagram and then what this part was for this part and then how he made this part and then how it all keyed in together, all the
Different chemical reactions.
Okay, so you got all that? Okay, so here's number 1. You need to do 5. Okay, so 1, you can go to Looper, I think that's how you spell it, it's lab, at University of Utah. And read there, and you'll be able to read what that research was about, okay? So you saw Kyle's thing, and what all the different drugs, and write up. So these are 1-paragraph responses, okay? So that's one that you can do. It's just a 1-paragraph, what you thought about it. Put 1 sentence in there that tells me that you gave it some thought. Okay? So if your paragraph is so generic that it would work for any seminar ever, then I probably won't give you the points. But otherwise, you get the points. Okay? Number 2, I'll link up, is Dr. Einstein's faculty lecture talk. It's on the web page, but I'll put it on to our Canvas page. So it's a lecture that he gave to the faculty a couple of years ago, and it's about stereochemistry. Okay? So that's number 2. Number 3 is, I believe it's this Friday, there's a math CS talk. CS talk. And it's supposedly more not for the general public, not just for, I don't think it'll just be a bunch of equations. Okay? So those are 3 options of the 5, and then we'll get a couple more. I've got a student that just got his PhD, wants to come back, give a seminar. So we'll do a few more, and then if we run out or you're gone or you miss these, then I'll link up some online ones that you can do. Okay? But the point here is just to get you to think about science in a broader way.
How many would you like us to do?
5.
5.
On that Friday one, are you going to put like what time and where and all that stuff on the canvas to attend it?
I can, if you can make it. It's out on the TVs, I think, currently. Have you gotten an email on it or anything? Hope it wasn't last Friday. You got one? Was it last Friday?
It was actually this morning, I think.
Oh, but the...
Yes, webinar. Is that what it's called?
No, that's a different thing. I'll make sure you get the email about it. Okay. All right. Got all of the... We're on level playing field now. Okay. What's Boston going to do? They're going to lose. Too. They have a season like that and then just get swept in the playoffs. I'd just be so nice. All right. And knock them off if the Dodgers get there. So. All right. My Rams are undefeated. So you got to wait a long time for that. Denver fans in here?
Yeah.
Man, we should have crushed you so much harder.
I thought, to be honest, I thought we would have.
Gosh, I was like upset at that.
To be honest, yeah.
All right, that's all good. Okay, other things, other questions? All right. Remember the goal of this class. What's the goal of this class? What's the goal?
Get educated.
Ooh. To medical school, to graduate school. They may want you to know something when you get there, too. You may be surprised. You may have to take pharmacology. All right. I don't know what... Did Kyle mainly talk about acids and bases? Okay. All right. All right, so I'm going to give you kind of a little mini lecture here. So we're going to go quiz on Monday, right? But I may start chapter 6 on Friday. Okay? All right. So, chapter 5. And this is reactions and mechanisms. Mechanisms. Okay? So, you'll see stuff like this a lot. You know, I've already done this thing. So, energy controls everything. There's two courses that if you're a chemistry major you'll take thermodynamics and kinetics, and that controls 90% of all of 99% of all chemical reactions. Okay, you have a couple percentage in there of like maybe you didn't. I didn't really emphasize this much, but that nitrogen has 4 different things attached to it. So it's chiral. It's a chiral nitrogen. But nitrogens are not chiral because it can these electrons can end up on the other side of nitrogen. Okay? So if you go to all the trouble to make a chiral nitrogen, you make it, and it's no longer chiral. Not in a second, not in a nanosecond, in a unmeasurable second. Okay? Because those electrons tunnel through the atom to the other side. Okay? That's quantum mechanics. Those electrons, because they're so small, they have no weight, they're more like a wave, they tunnel through the atom to the other side, and it racemizes nitrogen. Okay? That's the other 0.9%. The rest is controlled by energy. Okay? Energy is going to control, what we're talking about here is when you are 12, you can eat anything and everything, and you're so active, you have to be active, and your metabolism is so high, things are changing, that if I were to eat that as a 52-year-old, I'd be 700 pounds. That's all thermodynamics and kinetics. Okay? Metabolisms change. Speeds of reactions change. Okay? Those are all controlled hormonally. It's why we send 18-year-olds to war and not 35-year-olds. It's all mainly 18-year-old males. They're the best because their frontal lobes are not everything's kicked in yet on a hormonal basis. Your frontal lobes aren't developed fully, so you will charge that hill even though you may die. Okay? But, right, I got a couple of folks that have been in the military here. That's kind of but you do also need, those frontal lobes to develop later in life as well. So those are all controlled, and everything is controlled by a organic reaction and mechanism. Doesn't matter what it is. And most of the research that is done is trying to figure out why a reaction happens the way it is. Okay? So Dr. Chase's entire research project is to figure out why and how, well, it was, now it's a little bit different, of how alcohol is oxidized to retinol. With the alcohol play of how vitamin A is oxidized to retinol. Those are just chemical reactions, but they control an awful lot of stuff. That controls everything from, she used to work with fetal alcohol syndrome, to cancer, to reproduction now. Okay, it's the same. If we can figure out that mechanism, those mechanisms, we'll be able to know lots of things about diseases and how things work. So here, you start with something, okay? Here you start, here you finish. Okay? It's not a race, it's kind of like a race. And this is just a reaction. Okay? The energy difference between here and here is thermodynamics. Okay? So I'm gonna explode a nuclear weapon. You start, you explode it, you calculate how much energy comes out. Okay? I'm gonna light a Bic lighter. You start, you figure out how much energy comes out. Right? You maybe did these labs in GChem. Did you burn a marshmallow and figure out how much energy was in a marshmallow? Oh man, that's such a good lab. The Cheetos are the best. Okay, so in high school or somewhere, and what did you do? You calculated how much energy is in a Cheeto, right? I don't see any. You guys must have just had lunch. I don't see any like food laying out. But everything has a calorie associated to it, right? I mean, even if it's 0 cal. So this, see, I can't. It's hard to find 0 cal Gatorade. This has 30 calories, so that's not bad for me because I'm 52 years old. But those calories are the difference here. That's what that is. Okay? It calculated how much energy that is. How it goes from there to there, that is kinetics. That's kinetics. Okay? Because if I'm going to go from here to here, let's just say that takes 1 hour. Okay? It takes an hour to do that. Anybody got on the treadmill and watch how many calories you burn? That's horrible. You run and you run and you run, it says 10 calories. You're like, you got to be kidding me. Right? But that's just the rate in which an average person burns those calories. Some people may burn more, some people may burn less. That's the average amount. But that's the difference between there and there. But if you start running faster, you'll burn more. Right? So the rate in which you go from there to there is kinetics. Okay? So that's the rate, how fast it happens. And you can change that. I've got this really, really big peak here right in the middle. So if you're a couple of molecules and you got to go up over that barrier, think, man, made it over that one. Feels good. I'm going to slide down into this little thing. No, I've got to have enough energy to make it over that one. Oh, now I got to slide down into that one. Now I have to have enough energy to make it over that one. Well, if I don't have enough energy to make it over that one, it doesn't happen. There is no reaction. It just sits there. Okay? So you can do things to change reactions. You can say, I'm going to throw a third molecule in, which takes that barrier and moves it down. Okay? That would be a catalyst, or in biochemistry, an enzyme. Okay? Without an enzyme, without that change in rate, you could take in all the food you want, it will not metabolize. Because we don't metabolize like the Cheeto that you put in the fire and burnt it, right? You got all that heat off of there? That's not how we metabolize things. Otherwise, we'd be like, on fire. We metabolize things by lowering these energy barriers to a place in which we can run all of those reactions at 32 degrees. Is that right? Body temperature? 32 Celsius? 37 Celsius. Okay? So that's just how it works. At 37 Celsius, you have enough energy to run all those reactions. Okay? All right. So the how you get there is kinetics. It's also the how is also the mechanism. Okay? That's A plus B goes to C, but how does A plus B come together to go to C? That's the mechanism. And knowing all of those energy diagrams of each and every step in the mechanism is really, that's about most of what people research. Okay? So in this one might have 1, 2, 3, 4, 5, 6 different mechanistic steps to go from whatever that is to the other thing. Okay? Some may have 100. Some may have 1. So that's just, in general, how we'll do that. Okay? some point, I hope you realize that you're not going to remember the details. Down the road, in a year, I forget the details. I mean, there's something that comes up, I got to go look that up. But if you learn, I'm going to test you on certain details, but I could test you on details that would fail all of you. Okay? I mean, we've all had those exams, right? I mean, I could make what field do I want to pick on? Field that should be easy, but they make it incredibly hard. What is that?
Physics.
Oh, well, I think physics can be really hard, though.
Oh, no, it should be easy, but it's super hard.
Okay. Well, they don't make it hard, though. They're just like, they're trying to. I'm thinking of like when I got a C in Point Loma's version of kinesiology. I mean, the person made that course so incredibly detail-oriented that, I mean, you had to memorize every little tiny thing to get an A, and I just didn't want to put that much effort into it. So, but I want you to think about the big picture. Okay, so you've got to know the big picture, and you got to know the big picture for the rest of your life. You can't forget the big picture because we're going to stamp you with a degree that says you know the big picture, and know a lot of details underneath that. But the big picture is important to grasp. Okay, very important. Okay, if not just to impress your grandma at Thanksgiving. Talk about what you're learning. All right. So we're going to do a whole series of reactions. I'm not going to go over them right now. But maybe you saw some of those reactions with Kyle on last Friday. Talking about a whole bunch of different transformations of chemicals, right? We've got oxidations, we've got reductions, we've got substitutions, we've got eliminations, and you're going to learn all of that stuff. You're going to learn it, and actually, probably everything that he showed you, you would have seen in some form in this class. I looked over his notes. It's just with different molecules, okay? And you saw a lot of stereochemistry, right? Did everything in there have stereochemistry on it, right? And you had to control the stereochemistry and the reactions here to there. Did you guys say that was just totally wigged out? Or just say, hey, that's kind of cool? Because you can get there if you want to. It's not some huge thing. It's a big barrier, but you can do it. What's that? If you want to, right? There'll be other barriers.
If I could have a catalyst to make it easier.
Oh, yeah, that's what I am. I'm the catalyst. All right. So, so one of the simple reactions that we do is just an acid-base reaction. Okay. And I don't know how far he got into this, but really what I want to talk about is, let's say I had this acid, okay, and I react with a base, a weird-looking base, okay, KCN, and I have an equilibrium. These are all equilibriums, really. And I get, that's a minus charge. I guess I should put all my electrons here. Okay, plus HCN. There's a K here too. Okay. Pretty simple reaction. Do not do this reaction. Okay, you will kill yourself. But it's a simple reaction. So HCN, you take potassium cyanide, and it's a solid, and you ingest it, you're going to die. Okay. HCN's a gas, so as soon as you do this reaction, you're going to breathe the gas and it's going to die, and you're going to die. So you don't want to do that. But what would you do? Let's just say you had KCN poisoning. What would you do? All you pre-medders in here, don't answer. Anybody know why KCN is dangerous? Why it's toxic? Anybody? Why cyanide is toxic?
Does it mess with like the contractions like in your muscles and stuff like that?
No. You know how oxygen binds to hemoglobin? Right? So in high concentrations, oxygen will bind to the iron, and in low concentrations of oxygen, it releases, right? Or there's a term for that, cooperative effect of binding or something. Well, potassium cyanide does that too. It binds to the iron of your hemoglobin, but it doesn't come off. Okay, so how would you treat someone that ingested hydrogen cyanide or cyanide?
You have to find some way to force the cyanide out, either through chemical reactions or pressure, hyperoxygenation.
Oh, what? Say again?
Hyperoxygenation.
Hyperoxygenation. Yeah. So put oxygen on them. You can put them in a barometric chamber and pressurize them with oxygen, trying to get as much oxygen possible in there. Right? These are all properties that you've already learned. Right? Le Chartier's principle. Try to get that cyanide off. What's the other? That's if you're slowly failing. Then what do you do? What's the next treatment? Not out on the field. Blood transfusion. That's all you can do. Blood transfusion, and get that blood out of there because that cyanide is holding tight. It's gonna take a lot to kick that off. And so you just doesn't have enough energy to kick off that cyanide. Okay. All right. So don't do this reaction. We had. You remember that in grad school there was a person that was going to run a reaction like this, not this one, but HCN was going to be given off. And so they ran the reaction, told everybody in the building they were going to run the reaction, mixed it all together at like 1 a.m, shut the hood, told no one was around, no one was allowed to come in the building, and the next day the reaction would be gone. All the HCN would have gone up in the hood and out. The next day, they came in and found all the dead pigeons that were up on the roof lying around. So it took care of them. They didn't anticipate that, but but they knew the reaction worked. So, all right. So this is an acid. Okay. This doesn't look like a base, but it is a base. Okay. It's just not a real strong base. It's a weak base, but it's still the base. This is the conjugate, and this is the conjugate in this reaction. Okay? So this is where you're gonna. This is where I'm going to help you out. Here's where I'll be your catalyst a little bit here. So this is on this side of the equilibrium. You're going to call these conjugates. So you're going to say, is that a conjugate acid or is that a conjugate base? Well, just look at it. Is it an acid or is it a base? It's a base, so that's a conjugate base. Look at that. Is that an acid or a base? It's an acid. It doesn't look a lot like an acid. It's a very weak acid, but it's a conjugate acid. Okay? So, if you can learn this, all these reactions work. Okay? So, we have this equilibrium arrow here. Okay? We have that equilibrium arrow. If the arrow is big going that way, okay? Big going that way and small going that way, it is not because, it is, but it isn't. It's not because the acid is acidic or the base is real basic. Don't want to miss this one. So make sure you get this one. Make sure you get this one. All right. It's the stability of the conjugate base. How stable this thing is right here is going to determine that equilibrium. Okay? It's the stability of the conjugate base. So if it's really, really stable, that equilibrium is going to be on the right. If it's not stable, that equilibrium will be more on the left. Okay? So the stability of the conjugate base. Now, everything is in equilibrium. There's a theory out there that says that every reaction has a microscopic reversibility. So every reaction can be reversed, even if it's a microscopic amount. Okay? And that is, other than like huge nuclear explosions where it's pretty hard to take all that stuff and put it back into the bomb, we understand that everything just really kind of just goes back and forth. And all the reactions that we're going to talk about the whole semester and next semester, we're going to talk about reactions that go this way, and we're going to talk about them, and then, boom, I'm going to spin it around, and the reaction's going to go the other way. And you go, wait a minute, I thought the reaction went this way, or the reaction went that way. It's like they go both ways. It's just a matter of you can control through conditions which way the reaction goes. Okay? So, but for acid-base reactions, I can control this by, a lot of different ways. But let's say that I allow hydrogen cyanide to escape the reaction. Okay, that's going to pull the reaction even farther in this direction, right? Because you're losing that component. Or I could do the opposite, like the hyperbaric chamber, and I could pressurize it and put HCN in there. Well, that's going to drop it the other way and move the reaction that way. Okay, so you can do things to control the reactions, but naturally, on an acid-base reaction, it's the stability of the conjugate base in which is going to drive things. Okay? So, we have this thing called pKa. Did Kyle talk about pKa? He mentioned it once or twice? Okay. Okay. So the pKa is just a function, right? It's just a function of that equilibrium. So if the pKa, like for example, if I have hydrogen fluoride, HCl, HBr, okay, and hydrogen iodide, these are all, you'd think about HCl as a pretty strong acid, right? Okay, so its pKa is -7. I should make it a little chart here. Its pKa is -7, okay? Its pKa here is -9, and for HI, it's -10, okay? HF, anybody ever messed around with HF? Yes? No, you did not in lab last year. But if you did some glass etching, you may have messed around with some HF. Okay, you can be careful with it. But people that etch glass and make various types of paintings and things with glass, because it dissolves glass, you can't put it in a glass bottle. So everyone thinks HF's a really strong acid because it dissolves glass. No, it dissolves glass because of its properties, not because it's a strong acid. It's actually a pretty weak acid, has a pKa of 3.3. Okay? It's a fairly weak acid, but it's dangerous because it's so small. The fluoride atom is so small, it's nearly the size of a hydrogen, and so it penetrates everything. So what it does, if you spill it on you, it penetrates your skin, goes down to your bone, and starts eating away at your bone. Whereas HCl won't go through your skin. So what do you do if you spill HF on you? Huh?
Sodium hydroxide.
Yeah, try to get as much off, but it's already spilled on you. What do you think they do? Amputation? It'll do it on its own, probably. They actually take needles of sodium bicarbonate and inject it down into your skin to your bone. Needles of large amounts of sodium bicarbonate. Sodium bicarbonate's not that dangerous, so don't do that. All right. So why then is iodine so much of a better, stronger acid than hydrogen fluoride? It's much bigger. But the answer that you want to give me is the stability of the conjugate base. So what's the conjugate base of all of these things? It's the conjugate base is I minus. The conjugate base is F minus. Because iodine is so big, it doesn't even know that it's minus, that it has a negative charge. It thinks it's neutral, in fact. So it doesn't even care about that hydrogen. It says, psh, I didn't even know you left. Because the stability of the conjugate base. Okay? That's like if you're in a relationship and you don't know that the other person left for a week. Okay? That's HI. All right. We got a few more of these, but you kind of get the idea there. All right. All right. Any questions? Yeah.
Y has a stable base, correct? A more stable base?
Conjugate base.
So in HF, the molecules are so all fluorinated, so tightly packed together because of its electronegativity that makes it kind of unstable. Is that why?
Well, I mean, F minus. If you throw hydrogen fluoride, if you throw potassium fluoride in water, it will pick up. Some hydrogen. There's an equilibrium. It'll pick up some hydrogen. Okay. That's a big debate with fluorinating water, actually, because they'll say that hydrogen fluoride is super dangerous, and there is some percentage of hydrogen fluoride when you fluorinate water. But it's so small, and the equilibrium then becomes so small that it's not even detectable. But yes, the reason being is fluoride, you've got its nucleus and its filled octet is right there of the F minus. And so those electrons know that there's a nucleus. Okay? And so they're like, I don't want to be charged. I'm not supposed to be charged. So I got to find something like a hydrogen, okay, or a potassium or something. Whereas the iodine, its octet is way out there, and it doesn't even know it has a nucleus. That's the Gen Chem, right? That was from Gen Chem. Should have been. Okay. All right. Okay, lab tomorrow. Andrew's somehow really sick. What's wrong with Andrew?